Hello everyone. Today I will show our recent work called Watching on Your Phone's Back, Gesture Regulation by Sensing Acoustic Structure-borne Propagation. Existing works employs common built-in sensors such as microphone, accelerometer to sense typeset activity. They only focus on this coarse gesture due to the limited information obtained from the built-in sensors. Recent studies utilize sound propagators to enable a fine-grained gesture such as swiping, scrolling, sensing system on the surface of the commodity devices. However, this gesture regulation system relies on the in-air propagation, which can be easily inferred by other movements in the air. To the best of our knowledge, this is the first structure-borne propagation-based sliding gesture sensing research on the smartphones, demonstrating accuracy and robustness advantages that outlive native approaches based on the air-borne approaches. We propose a lower framework for discriminative gesture regulation. We designed extensive experiments to evaluate our system. So, in this page, we focus on describing the theoretical model of structure-borne propagation regarding the gesture performing on the back surface of the mobile phone. When the user touches the surface of mobile phones as shown in the left figure, the sound signal will encounter the figure. The part of the signals will be directly absorbed by the finger, and the other parts will propagate back to the microphone along with the reflection path. Therefore, the touch location information is related to the reflection path during the whole structure-borne propagation. The following paths are mainly described in the tails to extract the structure-borne components, which is highly related to the sliding gestures. For the further input, the structure-borne and air-borne direct propagation are separate because of the large propagation delay difference. However, we cannot directly identify the structure-borne and air-borne direct peak due to the random initial propagation delay. To combat the ambiguity, we perform a calibration scheme based on the property of the agency with these two components. To identify the structure-borne components, we use the algorithm to select the peak points corresponding to a structure-borne propagation and air-borne direct propagation to select the exact peak points. The one major challenge preventing precise gesture classification is the signal corruption. The fundamental idea of this model is to decompose the acoustic data into two parts. One part is the range of gesture patterns, but intensive to the user, while other part includes the user-related information, but intensive to the gesture. We propose a deep adversarial learning algorithm in order to learn pure gesture-specific representations, which is composed of three crucial components: signal decomposition, user-specific classifier, and a gesture-specific classifier. So for evaluation, we recruit 10 volunteers aged from 23 to 30 years old. All volunteers are asked to perform 10 gestures as shown in the figure and repeat 100 times with index finger. These two figures illustrate the comparison between our approach and other classifiers over 10 gestures and 2 situations. The result shows that our approach obviously outperforms all the baselines, including typical non-deep learning classifiers and competitive deep learning models, over all gestures and all situations. To have a closer observation, the confusion matrix of the dataset relative to the person who has the average performance over 2 situations are reported in the 2 figures. To study the impact of parameters in terms of the classifier model, we examine the system performing by tuning three important parameters, such as batch size, learning rate, and epoch. So the left figure shows the average regulation accuracy with different batch size and learning rate. The right figure shows that the training loss degrades gradually with increased epochs, and the degradation tends to coverage after 200 epochs. Thank you, that's all.